Hey, it's Mr. Lum again, and we're going to do some more acid and base chemistry. And today we're going to be looking at calculations involving Ka. So here we're given a question that says, what is the pH of 0.50 molarity of acetic acid, which is CH3COOH, and what is that pH? Now, if acetic acid was a strong acid, this question would be very, very simple because it would 100% ionize, and therefore, if it was 0.50 moles per liter, then the concentration of H3O would be 0.50 moles per liter. But this acetic acid is a weak acid. So even though acetic acid is 0.50 moles per liter, the concentration of H3O is going to be less. So what we need to do is calculate the concentration of H3O, and then with H3O found, then we can calculate pH. So let's get started. First thing we should do is write a formula. So H2O plus acetic acid, which is CH3COOH, and that forms an equilibrium reaction with H3O plus aqueous and acetate, which is CH3COO. Okay. Now, we know that, well, this is a liquid, so we don't really care about this concentration, but we know that we start with this concentration right here. Okay. Now, the concentration that we have with H3O is 0 and 0 at the initial. This is going to be change, and this is going to be, not change, and this is going to be equilibrium. Okay? So, this is going to decrease by a factor of x. This is going to increase by that factor of x, and increase by a factor of x, because it's a 1-to-1-to-1 ratio. So let's calculate this. This is going to be 0.50 minus x. This is x, and this is x. Okay. Now we're going to come up with a Ka formula, okay, which is exactly the same as KEQ, and that's going to be the concentration of H3O plus times the concentration of CH3COO minus divided by the concentration of acetic acid, which is CH3COOH. Let's fill in some numbers here, and if we look at our chart, we know that the Ka for acetic acid is 1.8 times 10 to the minus 5, so we're going to put that in. Okay, and that is going to equal x and x, or in other words, x squared over 0.50 minus x. Okay. Now, here's the interesting thing, is that, well, we could solve this using the quadratic formula. Okay, but we're going to be a little bit lazy and do a little bit of a cheat on this one. The percentage that's going to ionize here is very, very, very small. Okay, so what we can do is we can assume sorry, these are supposed to be S's. Assume that 0.50 minus x, we're going to assume that x is a very, very small number, and it's going to equal approximately 0.50. So this is what our assumption is. Okay? And so we can just put that right in here. So we're going to write assume here. You should always write assume to show the person looking at your calculation what you did. Assume, and this is our assumption right here. 0.50 minus x is just going to equal to 0.5. So that changes this to 1.8 times 10 to the minus 5 equals x squared over 0.50. Okay, I'm then going to solve for x, and that's going to be, well, if I solve for x, it's going to be root 1.8 times 10 to the minus 5, okay, times by 0.50. I times both sides by 0.50, and then I root both sides in order to get rid of this square root, and that equals x. Okay, and I've already done this calculation, and I found that x equals, here, I'll write this down here, x equals 2.73, or actually I should say 2.74 times 10 to the minus 3, and this is x right here, or molarity of H3O, so that's a concentration, so we can write that right there. Okay, and that's what our H3O plus is. Now we're not done yet, because the question asks what is the pH. Okay, so what we have to do is we have to take this number and put it into our formula to calculate pH, and pH equals the negative log of H3O plus. So we're going to take this number and put it right there, or in other words, pH equals the negative log of 2.74 times 10 to the minus 3, or in other words, our pH equals 2.56. Now, remember, this has 2 sig figs right here. Our Ka value has 2 sig figs. Okay, so this number should be 2 sig figs. It should be like 2.7. But I kept a few extra digits, and I'm just going to save my sig figs to the end. So this pH should also have 2 significant figures, which it does. Remember, after the decimal place is what is significant. So the 2 is not significant, the 5 and the 6 are. So this is 2 sig figs. I know it looks like 3, but remember, please remember, it's 2 sig figs. Okay, so 2.56 is our final answer. Okay? Okay, let's try another one. Okay, if you want, you can try putting the video on pause and see if you can do this question and see how my answer compares to my answer and my procedures compared to with your answer and your procedures. Anyways, the question says, what mass of NaHSO3 must be added to 1.75 liters to get a pH of 3.5? First off is, let's write a table. Okay, so I'm going to write HSO3. Remember, Na is in column 1, so this is going to be a spectator ion. Okay, so this is going to be our HSO3 is going to be our acid. So HSO3 minus is going to combine with some water and make, well, it is weak, and it's going to make H3O plus and SO3 2 minus. Okay, I'm going to fill in an ice table. Now, so this is going to be our initial, our change, and then our equilibrium is going to be down here. Now, we do not know our initial concentration of HSO3, nor do we know our initial, well, we do know our initial concentration, because when you first add this, the initial concentration of H3O is 0, and same with this one is also 0. Okay, but we don't know the initial amount of this. Okay, but we can find the H3O plus at equilibrium, because we're given what the pH is. The pH is 3.5. So if you want to find out the concentration of H3O, the formula is 10 to the minus pH, take the negative anti-log of the pH, and that is going to equal our H3O plus concentration. Okay, remember this is 2 significant figures. Okay, so we're going to go 10 to the minus 3.50. Okay, and that equals, I already calculated, and that is 3.16 times 10 to the minus 4. Okay, I know this is more than 2 sig figs, but I'm just going to keep a few extra numbers for our calculation until the very end, and then I'll figure out sig figs. Anyways, so at equilibrium, this is going to equal 3.16 times 10 to the minus 4. It's a 1 to 1 to 1 ratio, so I know that this is also 3.16 times 10 to the minus 4. That means from 0 to get to this, it had to increase by 3.16 times 10 to the minus 4. Okay, and that means this one had to decrease by this. Okay, we don't know what it was, what the initial concentration was, so we're just going to write x. So at equilibrium, it's just going to be simply x minus 3.16 times 10 to the minus 4. Okay, and we can make a Ka expression out of this. Okay, so our Ka, again, is going to be H3O plus times SO3 2 minus, and we are going to divide by, remember, water is a liquid, so we're not going to count water, and we're going to divide this by HSO3 minus. Okay, now we're going to fill this in with a few numbers, like this one, 1.0 times 10 to the minus 7 is our Ka value. And this is 3.16 times 10 to the minus 4, and same with this one. So we're just going to write 3.16 times 10 to the minus 4. And since it's two of them, we're just going to write squared. Divided by, well, this number right here, which is x minus 3.16 times 10 to the minus 4. Okay? Now, it's going to be a little bit difficult to solve for this one, but you can do it. Okay? And you could solve for this one right here. You times 1.0 times 10 to the minus 7 times this and this. Okay? And what you should come out with is, well, I already solved for x, and I'll save you a really big long calculation, and I'm just going to say x is equal to 1.0, this is going to be 2 sig figs, 1.0 molarity. Okay? So, okay, I just skipped a whole bunch of steps and I just solved for x, so you don't have to see me fumble around with some of the math there. Now, so x is also our original concentration of HSO3. Okay? So the question doesn't ask what our original concentration is. It says what mass of NaHSO3 it is. So we have to include that Na when we do figure out the mass. So we're going to do some basic stoichiometry here, and we're going to go 1.0 moles per liter of NaHSO3. Okay, we have to include that Na there, and we're going to change this into moles. So we're going to times this by 1.75 liters. Okay, and then we need to change this. So now we're in moles of NaHSO3, and now we need to change this into grams of NaHSO3. So what we're going to do is we're going to times by the molar mass. Na is 23.0, H is 1, S is 32.1, and oxygen is 16.0, and oxygen is going to be times by 3. But the molar mass, if you add all of those numbers up, it should equal something like 104.1 grams, and that is equal to 1 mole. Okay, and I've done this calculation already, and this equals 182 grams of NaHSO3 minus. And so remember, this is 2 sig figs, 3 sig figs, this is 4 sig figs, and therefore this is 100. This needs to be 2 sig figs, and that means this has to be 180 grams. Okay, and that's 180 grams, that's 2 sig figs of NaHSO3. Okay, and that's our final answer.